Okay, so we're gonna talk about fundamental limits of information systems. So what I'm gonna do is talk about a computational approach or computer-aided approach. So there's the outline of the talk. First, to give an introduction of the information system, the information measures. I'll compare two kind of approach. The first one is the more conventional. The second one is the new one. Then I'll go into a little bit detail on 3 example problems and finally the conclusion. Okay, so what are we talking about here? We're talking about information systems. So this is like a very general kind of circle we're drawing. It can be data compression, storage systems. It can be wireline. It can be wireless, I guess, although I'm not going to treat that. It can be crypto system, interactive computing, all kind of things. And we're also only talking about fundamental limits. So this is a hard limit. That is, no matter how smart or what kind of resource you have on your computation, this is the limit you cannot go over. So for example, for data compression, we know that you cannot compress to less than entropy. For communication, Shannon says you cannot suppress the channel capacity. Network coding, they cannot communicate about the mean cut. Interactive computing cannot beat the communication complexity. A little bit of a review of Shannon's information measures. We're talking about entropy. So this is from pretty much from the second chapter of Cole and Thomas. So a bunch of well-known inequalities. So first, non-negativity of we're talking discrete random variables. So non-negativity. Chain rule, conditioning reduces entropy. There is also the independence bound, the data processing inequality. So if you check the book, everything is in the second chapter. So there's pretty basic things. But as long as you know this, you can actually try to derive some fundamental bounds, fundamental limits. So for example, this is a well-known butterfly network. So sometimes people draw another node over there. So what you can write down here is you cannot, the joint entropy of the two cannot be larger than the cut set, which I only label those 3 there. So this is only using the inequalities I gave on the last slide. Okay, so how did I write that? So if you look at literature, this is more like art instead of science. So what we do is we look at, so this is the problem. You draw the graph. You say, okay, well, this is a coding problem. Let me think about it. You think about it, and you say, okay, well, there might be something I need to take care of. Then you start to write the inequality. You write inequality, try and error. Well, things eventually work out. So this is usually how people do this, my understanding, okay? This is I guess this is a nice way of seeing things. There's another way of saying this. It's called hiring a smart graduate student. So because of that, sometimes you heard people complaining, my student is not smart enough. He really needs to spend more time on it. So those are kind of, joking aside, this suggests that the approach we are using right now has a heavy reliance on human. So you need human ingenuity and effort. So the question I want to ask is, can we actually reduce the human factors somewhat? So the idea is simple, right? We have computers right now. So the derivation of the chains of inequalities, in a sense, you can view it as optimization problem. There are many possible information inequalities. What we are doing now is just say, okay, let's combine them somehow, eventually get a bound. That's all we're doing. So we're going to use computer to do some of the work. So the key driver here, why I think this may be possible, is that there are recent development in optimization software and hardware. Now I can't help it, but this is recent news, right? The AlphaGo program, so you can actually beat a human master on the game of Go. And well, I'm quite excited. This is going to happen again next March, this March actually, right? The game versus Lee from Korea, right? So if you think about it, this is a really difficult thing to do. If you can do this, can the computer actually write this? This is too simple, right? The computer surely should be able to do this. So what I'm going to try is to say, okay, well, paper and the pencil is too difficult. Let's use computer. So I think this drawing actually I got it right because I'm saying the computer is standing, on my side instead of in front of me, like fighting each other, right? So we're asking the computer for help. Question: has anyone actually thought about this already? It's hard to find anything like nobody thought of at all. So let's see. So Riemann actually had this linear program to prove information inequalities. So the question this program answers is this. If I give the program an information inequality, he will answer, is this inequality true or I cannot determine. What it uses all the inequalities from the basic properties, so we call this Shannon type inequalities. Those are all linear inequalities, so you can form as a LP problem. Do that, and you get the answer. So of course, we now know there are indeed non-Shannon type inequalities, so those are not the whole story, but somewhat surprisingly, if you look at the literature, most of the results on kind of practical coding problems, they're all proved by just Shannon type inequalities. So there are some results that you can say requires non-Shannon type inequalities, but it's kind of people reverse this search that it's not. We really need that for this specific problem. So there is also the software which has been online since 1997. This has been used in, I think, mainly two purposes. So people use it for investigation of entropy region, or probably more accurately say outer bound of the region. Or Riemann told me that he actually personally used it as auxiliary tool to say, okay, if I think this inequality is correct, I can check it. So he personally used that. So it's like an auxiliary tool for confirming simple conjecture inequalities. Now, it has not really been used very widely. I mean, this is really nice thing, right? Why it hasn't been used widely? So the first problem is this LP formulation is really complex. It's exponential in the number of random variables. For example, the thing I showed, the butterfly network, you actually need 9 random variables. So this expanded to 511 LP variables and that many constraints. And for a very simple problem, you quickly run out the range that we can handle. So for example, I tried a couple of things. I think it's like if you have less than 15 random variables, maybe, if you're lucky. Larger than that, usually just the ITIP will just stuck there, do not say anything. And the second problem I think this approach is it is an inequality prover. So, I mean, how do we come up with the inequality? Right? That's the first question. So engineering problems, what we want to do is find the fundamental limit, then prove it, right? But without a conjecture, there's nothing for us to prove. So how do we find it in the first place? See, we're stuck in this, Homer, stuck in this rock and hard place. And the third problem I see is kind of, this comes from a conversation I had with someone when I was working on this. So I said, I might have a method to work out some problem. And so this is a senior person in the community. He sort of say, well, okay, so maybe it's fine. So what's the big deal if we can use such approach, right? So I can understand what he meant by that, because there seems to be a disconnect between information inequality research and the coding problem research. So people in information theory inequalities come up with new inequalities, and they're all nice result. The relation with group, all this thing, very nice. But people working in coding, they just use certain type inequality, derive bound. That's it. So now for me, I guess you can call me, in this audience, you can call me actually a practical person. This rarely happens, actually. But if let me think about it, I'll say, okay, well, if we look at engineering problem, what I want is some kind of insights for me maybe to solve this engineering problem, or at least if you cannot solve it, maybe you can produce a readable proofs, present it to other people so other people can read it. Or, that's the third thing, useful to other researchers, right? So this is the approach I used. I will explain later on a little bit more detail. So it started about 3 years ago. Oh, actually, well, 3 years ago. So what I did is I first used symmetry and some other factors to reduce the IOP scale, and then try to find the kind of a trade-off region or whatever the region we want to characterize by scanning its boundary. Then form the conjecture. Then I use LPDU to actually generate a human readable proof. So I'll use the first example to explain how this is done. Then I'll present some new results. So I did get new results and important insights from all of them. All right, so this is the problem, the regenerate code problem, exact repair regenerate code problem. This shows up in this workshop many times. I probably don't need to go over it, but let's still do that. So you have a data is encoded and put into n nodes. Each node will have alpha storage. When a node fails, you want to repair it, and the way you repair it, you kind of extract a beta amount of data to this new node, and you recover it. All right? And what you access is D remaining nodes, any of the D remaining nodes. So the fundamental limit is between this alpha and this beta. So the difference between exact repair and functional repair is, in the original paper, Demarcus said, we can use the functional repair. That means the recovered content can actually differ from the original one, as long as functions as before. For the exact repair, its content on the new node is exactly the same as the failed node. The first, the one on the left is difficult, or the one on the right is simpler, but the one on the left is more practical. The one on the right is, I don't think any system engineering will want to use it. All right. So the result given by Demarcus said there is a trade-off. There is an explicit solution, so you can plot it. So this is the case for n equals 4. So to do that, you have this nice trade-off region. Because exact repair is a more stringent code than functional repair, so what we know that for the exact repair, it can only somewhere inside this region. So the open question that was not solved was, can actually they do the exact same thing? So there's some efforts before I look at it, but it was not completely settled. So using this computation method I was talking about, we can actually show this for the case of 4, 3, 3. We have the exact region is like that. The functional region is like that. So there is there's a separation between the two. So the exact repair optimal trade-off is not the same as functional repair optimal trade-off. So that's the result. So the interesting thing is, I guess, it's how I got this result. So I break it into 4 steps. So the first step is want to represent this as kind of information measure problems. So we gave all these things a name. So what's saved here is W1, what's saved there W2, W3, W4. The repair information is S12, S32, S42, send to repair node 2, and so on and so forth, right? So a bunch of random variables. You define this, you can come up with bound. The original information is given by B. This one has to be smaller than alpha. That one has smaller than beta. And the reconstruction requirement, the repair requirement. This is also the repair requirement says this guy has to be the function of all these 3. Right? So that way we can repair it without error. And the last one is saying any 3 of the node can be used to recover the original. So just write down the information equality using the problem structure. So we do that. But this problem is, I actually tried, it didn't work out, because it's actually too large. So the first reduction I use is symmetry. So The detail is kind of omit, but if you think about it, there should be no loss in using, actually, Kenneth talked about this. Okay, so there's no loss in considering only symmetry codes. So if that's the case, then a lot of quantities are actually repetition of each other. For example, this joint entropy, if I change the index from 1 to 2, 2 to 3, 3 to 4, and 4 to 1, then it should be the same as that one. There should be no difference between those two. And there are other reductions. For example, I already mentioned this. This one is B, but that means anything, a superset of this guy has also the entropy B, right? So those are actually not variables anymore. They are fixed numbers. So now we do the substitution in the LP program. So they are not useful anymore. You reduce that. And the reduction is quite significant. So originally, I had this many variables in the LP, this many constraints in that LP. Now, after that reduction, you only have this number and that number. So this is trivial for any modern solvers. So you put into this, what I did, I put into this Cplex and asked it to solve it. So I fix this B and fix the alpha and try to find the smallest beta. So you can scan out the kind of the region. So it's something like, you get a bunch of points, right? So if they are fine enough, you get this curve. Okay? And turn out I only need to prove this inequality there. And at this point, this is only a conjecture. It's not really a proof yet. The reason is I actually fixed B, right? I fixed alpha, so it's kind of an instance. It's not really a proof. So how do I actually prove that? But this is also not too difficult. So what we do is this. So think about why people are writing down as a chain of inequalities. There's actually no good reason to just do that. What we are doing is essentially this thing. So we know a bunch of inequalities. We want to apply them to prove eventually this inequality. Okay? And if you look at this closely, you can come up all kinds of different methods to do that, but it's simply the linear combination of them. So as long as I have the linear combination, I find the proof. So the essence of this is a linear combination for known inequalities. So that I will have to find those linear coefficients, but the LP solver already knows that, right? So I should just ask the LP solver, give me that number. So how do I do that? You can embed this problem, so kind of the dual problem inside the LP, and find the coefficient. So there is a kind of minor, this shouldn't be saying minor, technicality there. So if you do that, the dual problem is actually LP dual is not optimization problem. It's a satisfaction problem, whether there's a solution or not. So there are actually many solutions. There are many solutions. So what do we really want here? So the end goal for me is after I find this inequality, I actually want to write down this proof. And the fewer number of inequality I use, the better. So in a sense, I want the sparsest solution. But there's no way to do that, right? So the sparsest solution is NP hard. So I converted to a IO1 norm problem, and this will approximately find the sparsest solution. So you get that number. So this is result for our problem, the n equals 4 problem. So the inequality I found is this, so those are the effective inequalities to prove this bound. And the dual give me those coefficients. So you add them up, magically canceled out, give you this number. I give you this inequality. And you can write it a different way. You can write it as table. Here, anything here is a joint entropy. And you can use that to write a bunch of chain of inequalities and make it longer, submit a paper. So that's what I did like 3 years ago, I think. So after it's been 3 years, so I had a little bit more time to work a little bit more. So this is a new result. Well, not exactly new last year. also last year. So, I did get some of the insights on this problem. For example, for this type of codes, partly motivated by the result, I have this layer code construction. And it's actually using the result I got for n equals 4, n equals 5, it is the optimal code. And there are several subsequent works inspired by the result, the 433 result, so Dersma, Sassi, Haran, and Tian, etc. And there is a recent, actually last year, so people are talking about if we restrict it to linear codes, what case? So it turned out the code construction I gave for linear codes are optimal. So at least I can kind of confidently make this conjecture for all n linear codes optimal for this case. But I haven't been able to prove that. So a few notes after I talked to people and thought about it. So if you think about the approach I used, this is really not a nice mathematical way of doing things. What I did was, okay, well, there is a region I want to characterize. I try to find one boundary point there, another one I try to figure out what the shape this is. This is very engineering, right? So what's the mathematically clean way of doing that? You can view this as a polytope projection problem, right? So what we had before is a linear programming. So the half space intersection is polytope. So it's very high dimension. What you want to do, you only care about alpha and beta 2 entropy term. You projection it onto that plane. That's the shape you want. That's the region you want, right? So that's all we want to do. And why didn't I do that? Well, if you look at this closely, this is essentially because we are using inequalities, right? So this is essentially Fourier-Moskine elimination. And the bad thing about Fourier-Moskine is very expensive. So the order of the worst case computation is this. So to remove d variables in a total of n inequalities, you can get this double exponential complexity, computation complexity. So there are certain type of accelerations you can find in the literature, but still that's very complex. Okay, so in practice, I think I check online and ask people, so that if d around 40, if you are lucky, you might be able to do it. So that's the kind of the max, the largest problem you can handle. So in contrast, LP is polynomial complexity. So there is a mark there. It's polynomial, so this is you have to quantify polynomial in what. So if you check online, there's more precise definition. But don't worry about that. So what are we talking about here? So the problem I was looking at for n equals 4 nodes, for general codes, the complexity, remember this one. So if without a symmetry and no other reduction, you get n equals this number, okay? And d equals this number. So you write it up there, there's no way of doing it. So if you use order reduction, you get this number down here. Oh, wait, divided by 4 down here. And you get 1d equals 174. So that's the number worst case. So bad, right? So there's no way we can do that. Well, I shouldn't say that. So there might be the case that we are too lucky. So I don't think that's going to happen. But unless you tried it out, nobody knows. So for me, the memory actually, if I do anything like that, the memory run out first. So that's why I use this kind of a dirty engineering approach of tracing out the boundaries and find the conjecture. Each LP actually now is solved in milliseconds, so it's very, very fast. Okay, so I said we use the symmetry in the problem. And this is, it's very vague, right? So I say, okay, it's symmetric. So to understand it, you have to have a framework, say what type of symmetry is there. So I think the right way of describing it is the group action, or you can use a permutation, the induced permutation, to look at it. So originally we have Sn, the symmetric group of Sn, mapping from 1 to n to 1 to n. So this induced permutation on the set of random variables here. So all the random variables induce that. So that's the first induced permutation. But what we really care is not that one. We care about the power set, right? So because it's joint entropy, so it's all the subset of this. So the power set. So that's the second induced permutation. So if you look at it closely, the first permutation, say this one, 1, 2, 3, 4 to 1, 2, 3, 4, 1. The first induced permutation is something like that, and the next one has this number of elements. So you can define that carefully. Fine. So now with that carefully defined, we can ask a quick basic question. After the symmetry reduction, how many effective joint entrophies are there? How many effective elemental inequalities are there? So this determines the size of the LP. So there is this so-called POIA theory. You can apply it here. There is a nice way of doing that, but what we need is a cyclic index function PG. For the base permutation is you can find it anywhere. It's something like that for n equals 4. But for the second permutation, you actually need to figure out yourself. So what is that? So if you look at the thing here, it's actually pretty nice. Each term mapped to another term. Okay, so after you calculate that, you get this number of entropy and this number of inequalities. So the way you can do this is actually pretty simple. The cyclic index says if you represent the permutation by the cyclic representation, say this is the cycle 1, 2, 3 to 1, 2, 3. Well, 1, 2, 3 to 2, 3, 1. 4 is mapped to 4. Then you can draw this nice square. And the way we're going is this guy goes there, this guy will go there, this way come back. So it's pretty simple to figure out the pattern there. That's why after this you get one cycle of length 3, one cycle of length 1 to 5 cycle of length 3, 1 cycle of length 1. So to do this, we can actually figure out what if I have n equals 5, 6, right? And those numbers are not very promising. But remember that for equals 4, I had this many number of quantities, this many number of inequalities. So it's not consistent with that and this. The reason is we are only able to analyze this reduction by symmetry, but not the problem-specific reduction. So there is also, so this is like from 65,000 to that is like 20 factor reduction, and there's another roughly 20 reduction. So both factors are important. You cannot get away with just one. And if you really don't care about this precise number, you can actually estimate it. So just divide it by the n factorial, give you a pretty accurate estimate. If you work in the group, you know why. Okay, but the last comment is, what we're doing is counting. It's not enumerating. So the difference is you can count, you can say, okay, there are so many different ways of writing it, but I have no way of actually directly enumerating them. So what I have to do is still go through each one and say it is repeated. Then I can get rid of it. So that's not smart. But I haven't found a way of doing that. So if you have any suggestion, I appreciate that. Okay, the second problem, code caching, is related to actually someone's talk. So this problem says this: if you have a bunch of files, n files, what you want to accomplish is to cache something at a user. Then, when the requests of the users are reviewed, you send out something to all of them to satisfy the requests. Okay, and the trade-off is in the size of a cache and the size of this delivery, right? So if you can think about it, if your cache is very large, of course you can save everything. You don't need anything here. If this is very large, you don't need a cache at all. So there is a trade-off. So what is this trade-off? So again, we need to write it down as a bunch of random variables. But the interesting thing is here you have actually more interesting symmetry. And if you look at this plot here, so the user are sort of equivalent, right? If you can switch the user around, that's the first type of symmetry. And the file sort of is, why should they be treated differently? So you can sort of switch here around. There are actually two types of symmetries. So write down that. You get the symmetry structure of the problem. The first, again, the base symmetry group has two, xn and sk, n file k user. And the first induced permutation group is now more interesting. There are a set of random variables, but now you can, they induce different permutation, now you can composite them, right? So they have a more interesting permutation group structure. And then we care about power set. So you can, again, use Poincaré theory, do that, and do this. But that's not the most important thing here. What I want to say is, if you look at the structure after playing with that, you realize that, okay, the demand for certain type of files is not the same as others. For example, if the first two users want file 2, the next user want file 1, and the last user want to file 3, this is similar to the first two users want file 3, the next two users want file 2, and the last user want file 1. But this is not the same as that. So no matter what you play with the symmetry, they are not equivalent, right? So now we have to be careful by saying what is symmetric solution. So the symmetric optimal solution exists, but only up to the symmetry we defined here. So using that, you can derive new outer bounds. Something like that is, in summation. So what's the insight I got here? So what I found interesting is this. For this actually outer bound is useful for code construction. Of course, we're only talking about outer bound, so it's useful only if we assume it's achievable. And then that's a big if, a big assumption. But for certain points, you can say, well, maybe it seems reasonable. So if you believe that, you sort of know where to look at. You sort of know, okay, this is the point I want to achieve, so I should look at construction for that point. And for me, I realized that knowing where to try is actually more than half the work. If you do not know where to try, it's just basically no way of doing anything. And actually, you have more information there because you have the proof. You can actually use the active inequality to try to extract dependence, independence, work dependence. So we managed to do that. So this is the original code proposed by Matali and Nissan, and we found a new construction sort of can achieve this. And this is in summation again. A third problem, what I call multi-level diversity coding with regeneration. So this is a combination of the two problems. First is regeneration code problem. Second is the multi-level diversity coding problem. So if you don't know that, well, don't worry about it. So you combine those two, you get a new problem. And what we want to do is for fixed B1, B2, B3, the rate of all the messages there, I want to find the trade-off alpha beta. So get some new result there, but the new thing here is that the trade-off, if you think about it, is not alpha beta anymore. It's actually a 5-dimensional object. So to trace out a region in the 5-dimensional space is a little bit tricky, so you need to do that more carefully. So the insights for that problem, so you can learn quite a bit just from the simple case. So the results suggest at the MSR point, the minimum storage point, so the trade-off there, the separate coding is actually optimal. And this will actually be able to show it rigorously. And MBR point is the same case, and we'll also be able to show it, confirm that. And for the n equals 4 case, there's one corner point seems achievable. And we did construct code for that and achieve the whole region. So this one of them is joint work with Tian and Chao. All right, so last slide, I think. So what we did was we tried to kind of help the conventional analytical approach a little bit by using computer. Reduce the human factor, but introduce more machine intelligence. This is what I want to develop is a more domain-specific LP approach. I tried it on several research problems, and it seems to be effective. Of course, I need to try more, I guess. what I want to say is that this is actually more than just a proof. It actually gives a lot of insights for code construction, and you can use that to kind of provide conjecture and also figure out fundamental limits. The main challenge, again, well, is still have complexity. No matter what I did, well, it is reducing from the exponential order by a certain factor. It's still exponential, so it's high complexity. But it seems we can squeeze out more, right? So originally, nobody thought we could do that, but after the symmetry reduction, we actually can do that. So there seems to be more to be squeezed out. And we need to kind of think more like, let a computer think more like a human. Some results are online. You can find on my webpage. So when I was reading this article, I cannot help notice what this leader, Google DeepMind leader, was saying. It says the system could process much larger volumes of data and surface the structural insight to the human expert in a way that is much more efficient, or maybe not possible for the human expert. So that's exactly what I felt during all this exercise. So I want to point it out. And that concludes my talk.